All right, week 7. We're in week 7, almost done with week 7. It's amazing. So today we're going to cover all of chapter 8. Don't worry, it is not as overwhelming as one would think, even though there are 46 slides, but it's okay. Some of them might go by super fast. Some of them I flip through pretty quickly. So we're going to talk about distributions of sample means and sample proportions today. So I'll explain what a sampling distribution is. I will explain what makes it normal, when we can do different types of things with it. So chapter 8 is kind of the foundation of 9 and 10, which are coming. So the stuff that we're using in chapter 8, we don't use it a lot by itself. I mean, we do a little bit. We don't use it a ton by itself. We use it more in conjunction with the things that we're going to learn in chapters 9 and 10. So it is pretty important as far as carrying it along with you, but it isn't overly complicated. So hopefully it'll be a little bit easier than some of the other stuff we've done. However, standard deviation still exists. We still use it. Mean is still there. Still talk about things being unusual, all of that stuff. We still talk about normal distributions. So as you guys may notice, my voice still isn't fully back. It was 2 weeks as of yesterday. I don't know what the heck's going on. So I don't know it. And then I just volunteered to read the names at the graduation. So I'd stand up there and announce people so that they can come up and get their diploma. I sure hope I have a voice by then. All right, so let's move on. We're going to start with sample means. We're going to start with means, and then we'll go to proportions. I'll let you know when we are swapping. Okay. So a sampling distribution is when we take every possible sample within a population of a certain size. So whatever that size is, the sampling distribution would taking all of the samples possible of that. Obviously, that's not always possible. So sometimes we just take a lot of those samples, and we're going to talk about what that looks like. So a sampling distribution of sample mean would be, I take all of these samples and I find the mean of each of those samples. Once I take the mean of each of those samples, I kind of ignore the actual data and I just look at all of the means. And it ends up being able to better estimate the actual mean of the whole population. So I take lots of little samples and then I put all of the means together in order to make estimations of the entire population. I'll give you some examples what that looks like. This is a lot of words. So the government wants to figure out what the mean income of all US households are. Obviously, they're not going to survey every single household. It just doesn't make sense. So what they do is they take a random survey of about 250,000 households, which doesn't sound like a lot, or it sounds like a lot, but when you think of how many households are in the whole US, it's not a terribly large amount. And then they took the mean annual income of that 250,000, and they got this number right here, the 72,641. They got that. It's right there. So then they take a second sample, also 250,000, and then they find the mean of that, and we get this. Then they do it again and get a third sample, and they get this. So they have all of these means now, and if they keep taking these samples over and over and over again, then they can compare all of those means or find the mean of all of those means so that they can estimate the population mean. And this is basically what a sampling distribution is. So since these all vary, it's still considered a sample mean, even when we find the mean of all these means, but it's going to be super close, and our standard deviation is going to be smaller because I found the average of each one of these. I'm going to show you the procedure for this, but obviously I'm not going to require you to replicate it or do this, but you'll kind of get an idea of what we're doing here. So the first thing you do is you take a simple random sample, whatever size that ends up being. I'm going to show you what happens with different sizes in a minute. Then you'll find the sample mean. We have a finite population. You're going to do it again. You're going to take another sample, find the mean of that, and then another sample, and on and on and on until you've gotten all of the possible samples. So once you get a sample, you can't get that same sample again. So all of these are independent and they're all different. Now, a data value can be in more than one sample, but you're not going to have exactly the same sample. I'm not going to choose the exact same 250,000 houses twice. That just doesn't make sense. So once we have all of those samples, then we take those means and we can find the mean of those means. And that's what we're doing today. All right. So we have the weight of pennies minted after 1982. We have they're approximately normal. The mean weight of these pennies is 2.46 grams. And I have a little bit of a delay today. The standard deviation, these are population values, population mean and standard deviation. So I took 200 simple random samples of size 5. So I took 5 pennies, I found their average weight. Then I got 5 more pennies and found their weight. And I did this 200 times. And I have all that data on the next screen. Don't worry, you don't have to put it in your calculator or anything. That'd be kind of rude. So here's all that. Nope, it's not there yet. So I'll show you. This is all the data right there. So I took 5 pennies 200 times, and I found the average of each of those 5 pennies. So this is kind of what it looks like. Here's one sample. This is 5 pennies that I chose. I weighed them, and then this would be one of our means, be one of the means for this sample. Okay, so this is all my data. This is all the means of all the samples. It's a lovely data, and this is sample size 5. All right, so of my sample means, I took the mean of my sample means. So I took all of those means, which is now my new data, and I found the mean of those. I got 2.46. The standard deviation of just those means is this, which is so much smaller than the standard deviation population. So we go back here. My standard deviation population was 0.02, and my mean of my population was 2.46. So these numbers, this is basically, I have the exact same as my population mean, but the standard deviation is so much smaller. The reason that it is so much smaller is because I took the average of those samples. So it's not all over the place. It is just the average of each of those samples. So here's a lovely histogram of my weights, or the mean weights, the means of all of those samples. It's nice and pretty. It looks pretty much normal. It's spread out a little bit, but it's not too bad. It's nice and pretty. So let's move on. So we want to see what happens when I change the sample size. This is going to become important. So I'm going to change my sample size. So this is an important thing. You're going to want to write this down. You're going to want to know this. You're going to maybe put star by it. I can absolutely guarantee you'll have a question somewhere that asks you this. As the sample size of the sample increases, the standard deviation of the distribution of sample means will decrease. So if I have bigger samples, my mean of each sample is going to be closer to the actual mean. Therefore, that standard deviation is going to get smaller. So I'll show you some examples, show you what it's going to look like. So here we go. So I'm going to try to use a sample size of 20. The last one was a sample size of 5. This is a sample size of 20. Look at this histogram. So the histogram is not as widely spread. It is looking even more normal. It's more bell-shaped. And now I have this standard deviation. This standard deviation is even smaller. It's like half of what it was for n equals 5. A smaller standard deviation is good because it means that the data is not so spread out. There's not such a big difference between the sample means of the means of all of my samples. So this is good. There's less variability because I have a larger sample size. Totally makes sense. The bigger sample size more accurately represent the When we are calculating the standard deviation of a sampling distribution, so when we are dealing with samples, we notice that this is not the same as my population standard deviation. It's because we have to look at things different. We have to take the sample size into consideration. I mean, just like, look, when my sample size was 5, the standard deviation was 0.0086. When it's 20, it's 0.0045. So obviously, the sample size means something here. So I have a new calculation that I'm going to give to you. This right here is the formula that we are going to use. So if I'm looking for the new standard, or if I'm looking for the standard deviation of my sampling distribution or the sample means, I need to take the population standard deviation and divide it by the square root of the sample size. This is called standard error. You'll see it called standard deviation. You'll see it called standard error. They mean the same thing. They mean exactly the same thing. I will frequently refer to it as the new standard deviation. This is what I will call it. New standard deviation. So if I'm answering your questions in like the forums or in messages, I'll probably say, you need to use the formula for the new standard deviation. We use this symbol. It's a sigma sub x bar. We use that symbol for the new standard deviation or standard error. For the mean, or the new mean, we're going to use this symbol. This symbol is for the mean of our sampling distribution. So that mean equals the population mean. So you don't have to calculate anything new. Notice when we took our data and we found the means of all of the means, it equaled the population. So the mean is just going to be whatever the population mean is, but the standard deviation is going to be this new formula. We're going to math it out in a second. Questions before I move on? Okay. So I took the population standard deviation, that's that 0.02, divided it by the square root of 5. So this is when we had a sample size of 5. My calculations gave me 0.0089. This is so close to what we found in our earlier example by actually calculating that standard deviation, 0.0086. I don't think anybody's going to be mad that we are 0.003 off. Then I tried it again with the sample size of 20. So once again, I have the standard deviation from the population, divided it by the square root of the sample size, and I got 0.0045, which is exactly the same as the standard deviation we found earlier. So this is how we're going to calculate it. So it's really important. You're only using this with samples, and you're not going to use it in questions that are just pulling one individual and asking questions about that. This is strictly for samples. When we're dealing with a sampling distribution, or we pulled a sample and we want to find something out. All right. Questions before I move on? All righty. So this is important stuff also. If a random variable is normally distributed, then the distribution of the sample means are also normally distributed. So if the variable's population is normal, then our sampling distribution is also normal. Sometimes, though, unfortunately, we have a non-normal population. We will have a population that is not normal. So that's going to cause us some problems, but not really. We're going to get there in a minute. Okay, so the IQ test is a measure of intelligence derived from the standardized test. Scores on this test are approximately normally distributed. That's important. That's good. With a mean of 100 and a standard deviation of 15. We want to find mu sub x bar, that's how we would say that, and sigma sub x bar. So remember, our mean is always the same as our population mean. It's going to use your new symbol, mu sub x bar equals 100. That's all we do. Just grab the population standard or population mean that they gave us and just run with it. But the sigma sub x bar, so my sigma sub x bar, it's the standard deviation, that the population standard deviation divided by the square root of the sample size. I should not have written n. I should have written a 9 there. Thankfully, these are nice, pretty numbers. I like it when they're nice, pretty numbers, because then I can just say 15 divided by 3. So it's going to equal 5. So this is our new standard deviation. This is the standard error or new standard deviation. Error or new standard deviation. So once again, we use this when we have samples. So then we can do whatever math we could say. We can do whatever math we need. So, and we'll do that in a minute. Okay, let's go back. Okay. The weight of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. That's old news. We want to know the probability that in a simple random sample of 10 pennies minted after 1982, we would obtain a sample mean of at least 2.465 grams. So what we're saying is, if I took a sample of 10 pennies, what is the probability that the average weight of those pennies is at least 2.465 grams? So first, we need to calculate the mean and the standard deviation here. So that's first. So my mu sub x bar is just the population standard or population mean, sorry. Mu sub x bar. You just take the population. My standard deviation sub x bar is going to be the population standard deviation divided by the square root of the sample size. I'm going to put this in my fancy schmancy calculator because I can. Because they didn't give us a pretty number. So it's approximately 0.0063. So that is my standard deviation. We already have the tools we need to calculate this. This is just using normal CDF, but because we're dealing with means, because we're dealing with samples, we're going to use normal CDF with this standard deviation. So at least means greater than or equal to. So we're looking for the probability that we get a sample mean of at least 2.465. That's what we're looking for. Probability that our sample mean is greater than or equal to 2.465. So here we go. Stop it. I don't know why my pen went away. So normal CDF. We want at least, so that my lower bound is 2.465. My upper bound would be 1E99. My mean is still the 2.46. And the standard deviation is 0.0063. Whoa. 0.063. So this is what we're putting in our calculators. Hoping you all put that in the calculator with me. Hopefully I put it in my calculator correctly. I think I did. Sometimes I typo. It happens. Yeah, okay. I got approximately 0.2137. So there's about a 21.4% chance that I would obtain a sample mean of at least 2.465. So it wouldn't be unusual, but not super large, but it's not unusual. Questions? I believe that all the math is like typed out on the next page, and I just wrote all of it down. I'd rather write it down though. So our textbook likes to convert everything to z-scores. I don't, that's not my style. I don't like converting everything to z-scores, but I mean, using the z-scores, they got a really close number. And as I've said before, your homework program, My Open Math, will accept it either way. So if I would have converted it to a z-score, I would have had approximately 0.79. Calculate that. I got 21.37. It's 21.48 with the z-scores. Same thing, basically the same thing. So you're still good. But as you can see, this is the nice, pretty curve all drawn on there and shaded in what we're looking for. Okay, let's do another one. So I would like you to try this. I'm going to give you a minute. I'm going to have you try this, and I will work quietly behind you. So once again, IQs is approximately normally distributed mean of 100 and standard deviation of 15. We want the probability that a simple random sample of size 10 results in a sample mean greater than 110. So we're looking for the probability we'd get a sample mean greater than 110. Do exactly what I just did, but with these numbers. I'm going to give you a moment, and I'm going to work quietly behind you. How'd we do? Do we get any answers? Oh, good. Good job, Megan. So see, it would be unusual. It would be unusual to get an average IQ of over 110. That would be unusual. Do you all know that you can do, I may have shown this to you before, I may not, that you can actually do math in your calculator function. I'm going to show you real quick. I may have showed you before if I did, good refreshers. Let me jump back to the calculator over here. Hopefully it won't move too slowly. Okay, so when I go into my normal CDF here, so I want 100 to be my lower, and my upper obviously is 1E99. My mean is 100. My standard deviation is, I need to do math to get that. I can do the math directly here in my calculator. I could do 100 divided by square root of 10. Is that what it is? Nope, sorry, 15. Let's clear that. 15 divided by square root of 10 right in the, right there. And it's just gonna use that for my value. So I don't have to actually do the math on paper, or if I don't have to worry about typos. Plus, I don't have to round because you're always slightly off when you round. So there's no rounding involved. And then I just put that in there. And what the heck? I did something wrong. What did I do wrong? Oh, I said 100 instead of 110. No wonder it's like 50. See, y'all don't tell me when I make mistakes. It's okay. Okay. It should have been 50. That was perfect. Okay. So that's slightly off because there's no rounding. It was 0.0175. It's because there was no rounding involved by putting that math in there. It's like one of my favorite features. I learned it by accident, but it's one of my favorite features of this calculator. See, there's a reason I call it fancy schmancy. Any questions about these problems before I move on?
Can you just explain the unusual part again? I'm kind of forgetting that part.
Yeah. Anything that has a probability of less than 5% would be unusual.
Thank you.
You're welcome. It's okay. So yeah, since this has a probability of 1.74%, it would be unusual.
Right. Okay.
Yeah. Good question. Anyone else before I move on? Okay. Whoa, I don't know what's going on sometimes. All right. If I have a non-normal population, this is just going to be super fast. If my population is not normal, for example, right here, I have a uniform distribution. Rolling dice is one of my favorite examples of a uniform distribution. So it's not normal. So I can't just be like, yeah, let's run all of the stuff with it. Let's do all the stuff. There is something called a central limit theorem. I'm not going to require you to memorize what a central limit theorem is. But basically what it says is that, that doesn't work. How come it doesn't show? How come it doesn't show? Oh, it does. Okay. So I'm going to show you what it looks like as I get my samples. So I'm taking this particular not normal population, and I'm going to take 200 simple random samples of size 4. Then I'm going to do 10, and then I'm going to do 30, and I want you to see what happens. So this is size 4. I mean, it's kind of normal, but I wouldn't, I mean, it looks like it's skewed right just a little bit. What happens when I do size 10? This is getting more normal. This is looking better. It was my uniform distribution. Sample size getting bigger. It's making it more normal. Look what happens when I have size 30. This is almost a perfect bell curve. It's almost perfect. So your important information here is this right here. If our and it doesn't say everything, if our population is not normal, the central limit theorem tells us that if we have a larger sample size, our sampling distribution becomes normal. So the rule of thumb is sample size greater than or equal to 30 is what we use with the central limit theorem. So if population is not normal, isn't normal, you need a sample size greater than or equal to 30. There quite possibly will be something like this on a question like this on a quiz. I can't remember, but I think there might be. So you don't necessarily need to remember the central limit theorem, but just remember that if you have a not normal population, your sample size needs to be greater than or equal to 30. All right. That is the important piece. I'll give you a moment if you're writing that down with my terrible handwriting. It's pretty funny. We have these little portable air conditioners that don't actually cool our classrooms down, but they make everybody psychologically think that they actually cool our classrooms down. So the teacher next door plugged hers in and it blew all of the circuits in my room, my classroom. So the only thing I had was lights. And the kids are like, oh, we can't learn now. We don't have the smart board anymore. We can't learn now. And I'm like, I have whiteboards. What did you think we did before all this technology? So I was like teaching them on whiteboards. They were pretty disappointed. They thought that the whole lesson was ruined. Like, nope. I'm an old lady. I can teach on a whiteboard.
Man, they'd have been disappointed with chalk.
I know. Tell me about it. It was pretty funny though. They just thought that it was like tanked. I'm like, no, I can do this. My first couple of years of teaching, I just used a whiteboard. All right. And look how fancy we are over Zoom with all of this stuff. This is pretty fancy. Okay. Yeah. What did people do while driving before cell phones were invented? Yes. I know it's like people like, how did you find places? How did you get information when there was no internet? You know, you went to the library or you just didn't know stuff. All right. So this is an application of this. You probably will find something like this in your homework. So the average time for an oil change at the 10-minute oil joint is 11.4 minutes with a standard deviation of 3.2. If a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. All right. All this is asking you is what is the mean and what is the standard deviation of your sampling distribution. So all it wants is it wants you to say that your mu sub x bar is 11.4 and your standard deviation sub x bar is 3.2 divided by the square root of 35, whatever that is. Whoa. So it's approximately 0.54. That's all they're asking when they want you to describe the distribution. They're not looking for you to do any math. This is where you do the math on B. If a simple random sample of n equals 35 oil changes is selected, what's the probability the mean oil change time is less than 11 minutes? So we want to know the probability that X bar is less than 11 minutes. So go ahead and put that in your calculator. Go ahead and try putting the fancy math in there. It's a good time to check that, to try that. So your lower bound should have been negative 1E99, upper bound 11, you do 11.4 for the mean, and then the fancy schmancy math. I got approximately 0.2298. Okay, so you guys didn't, I put the fancy math in there. Did you all put the fancy math of the 0.54? No fancy over there? Okay. Yeah, and my open math will accept either one, so you're good. Yep, nope, you're good. You're all good. So about 23% regardless. So you have about a 23% chance to get a sample with a mean time of less than 11 minutes. All right. So now we're in 8.2. If you keep track of that sort of thing, we are now going to jump to proportions. So just take your little mean stuff, take the meanness and set it aside, and we'll deal with that later. We're going to jump to sample proportions. So the idea is still the same, but we're going to be looking at it a little bit different because we're proportions. So set that aside, put on your proportion hat. There you go. See, I love it. Love the glasses. All right. So, this is our first P hat. This might be our first P hat. The sample proportion, all it is the number of successes divided by our sample size. We now call this P hat. So in math land, every time we put a hat on something, it is an estimate. When we are estimating a population proportion, we will call it P hat because our sample is an estimation. So X is your number of successes divided by your sample size, and that is a P hat. P hat is going to be with us for the rest of this class. So our population proportion is just P, and our sample proportion is a P hat. So there you go. And when my open math is not, doesn't want to make this fancy symbol, they will just write it. They'll just write it like this. That's still P hat, or it's fat, but it's P hat. So that's how my open math frequently writes it, just letting you know that it's a thing. All right. So a Quinnipiac University poll conducted in May of 2008. They took 1,745 registered voters and were asked whether they approved of the way George W. Bush was handling the economy. 349 said yes. So we're going to get our point estimate. Our P hat is called a point estimate. So point estimate, I'm going to write the words. Point estimate equals P hat. I don't want to write it like that. Okay. P hat, which would be the 349 successes divided by the number of people polled. That is not the number of people polled. Okay, so I'm just going to take 349 divided by 1745. So my P hat is 0.2. That's all it is. That's all the P hat is. It's basically a relative frequency. We just keep calling it different things. So just roll with it. But it is your point estimate. Okay. So I would like you to find this point estimate. I know you can do it. They conducted a survey of 1,000 adult Americans, age 18 or older. They said, are you currently on some form of low carbohydrate diet? 150 said yes. Go ahead and find your P hat. Get used to drawing a P hat on your paper. Oh man, people who don't come to these Zoom meetings miss out on the fun chat. Seriously, there's all sorts of fun stuff going back into the chat. It's awesome. You're missing out. So 150 divided by 1,000. I could do this in my head without the calculator, but it is Thursday evening after all. So this is just 0.15. So 15% of the people said that they were on a low carb diet. All right, we good with our P hat? All right, moving on. Let's actually start talking about our distributions. All right. So we're going to talk about the sampling distributions and look at some histograms once again. So, and according to a Time magazine poll in June of 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. We're going to look at the sampling distribution of sample proportions for all these samples. What the heck? I don't know what's going on here. I didn't hit anything, I swear. Okay. All right. So let's take a look. So here's what happens when we have a sample size of 10. Sample size of 10, we've got a little bit of a skew. A little bit right skewed. Sample size of 50. This is getting better. This is looking better. Definitely looking better. And take a look at our mean and standard deviation down here. So our mean is 0.426. Our actual population mean is 42%. All right, so now here, we're still at a mean of 0.426. Our standard deviation, take a look at this, it's getting smaller. Okay, so our standard deviation went from 0.160 to 0.072. Look at 100. This is looking almost bell-shaped. This is looking pretty darn good. And our standard deviation, look, our mean is now exactly what the population mean is. And our standard deviation is pretty small. Ours is 0.047. So the larger our sample size, the better our, the more normal our sampling distribution is. So this is looking pretty good. So you can exactly what we talked about, or what on your last, it was on our, I think your last quiz, maybe. As our sample size gets larger, our population gets more bell-shaped. So, all right. So, and this is all the key points from what we just talked about. As the sample size increases, the shape of the sampling distribution is more bell-shaped. The center, so our population proportion, our mean and our population proportion become the same. So take a look. The mean is our population proportion. So our mean, I'm going to write it like this, our mean sub p hat equals p. It equals that population proportion. Once again, we have to take into consideration the sample size when we are calculating the standard deviation of a sampling distribution. We're going to need to do that again. It's going to look a little bit different than when we did it with the mean, but it is going to, we still have to take that sample size into consideration, because as our sample size gets bigger, our standard deviation is going to get smaller. Or as our standard deviation gets smaller, our sample size has to get bigger. I'm going to give you the math for this in a second. Here it is right here. This is your magic formula. So once again, we are going to use the NP times 1 minus P is greater than or equal to 10. We are using this. This is how we tell that our population is normal. Or this is, as long as NP times 1 minus P is greater than or equal to 10, then we become approximately normal. So our mean is, as I said, the mean for our sampling distribution is just going to be the population proportion. And this is what we're going to use for our standard error or standard deviation. This is also called standard error. So it's just the square root of the population proportion times 1 minus the population proportion divided by n. And that will give us our standard error. I'll give you a second. I think they were just putting something on the door. It looks like it. Looks like they put some sort of a coupon or something on my door. All right, moving on. Okay. Also our sample values need to be independent. So we check our population size. Our sample size can't be more than 5% of our sample size. So that's another thing that we need to check. Check the sample size, check that NP times 1 minus P is greater than or equal to 10, and also check our, use our new standard deviation. All right. We're
Can
gonna-
you say that again about the 5%?
So in order to say that each of our samples are independent, so if I'm choosing, like, let's say my sample size is 20, but I'm choosing 20 people out of a room of 30 people, they're not going to be very independent. It's not going to be independent. It's not going to be very random because I'm going to be taking almost the whole class or almost the whole room. So my sample size has to be less than 5% of the entire population in order for my sample to be independent. So that's what this means right here. That's what this means. That means the N is less than or equal to 0.05 of the big N. Little n is your sample size, big N is population size. It's going to check all of this for you, but these are the things that we need to check. These are the steps that we need to take before we do this math. Call it the 5% rule. All right, let's do some math. All we're going to do here is describe our sampling distribution. We're going to calculate the mean and standard deviation. So once again, we have 42% of our people here. We took a simple random sample of 50 voters. That's why our sample sizes are 50. So we're going to describe the sampling distribution. Before we describe the sampling distribution, there's a few things that I have to look at. I have to look at the fact that 50 is less than 0.05% of all voters. This is how we can claim independence. It's less than 5% of all voters, therefore it's independent. I need to look at NP, so I need to look at this, NP times 1 minus P greater than or equal to 10. What that looks like is N, which is 0.42, times, that was my P, silly me, 50 times 0.42 times 1 minus 0.42. I need to calculate that so I can determine whether or not it is normal. I got 12.48. That is greater than or equal to 10. So I have a normal population. So once I check those two things, now I can calculate my standard deviation and get my mean. So my mu sub p hat is just going to be 0.42. My sigma sub p hat is going to be the square root of 0.42 times 1 minus 0.42 divided by 50. All of that stuff can go into your calculator. You might need some fancy parentheses. Uh-oh, I don't want that. Undo that. Stop it. Okay. I hit the wrong button. It did weird things. Okay, so this is approximately, my pen would not go away. It's approximately 0.06. Having issues. 698. So I got my mean and my standard deviation. So now if I needed to do any calculations, I would use these values for those calculations. Questions on any of the stuff I did here? All right. Hey, look at that. All the math was on the next page. 50 is smaller than 5% of the population, did the NP times 1 minus P, and then it shows me my standard deviation. It is really close to the standard deviation we got with our simulation. That was 0.072, which is awesome. Where did I get the 10? That's just part of the rule. So our rule back here, this right here, let me erase some things. Okay, so this rule right here, that's where the 10 came from. It's just a number that the creators of stats decided that they were going to use that number, but that was a good number. So if it's greater than 10, we're good. So yeah, it's just a number. You're welcome. Okay, let's do another example. So I'm going to let you do this and I'm going to work behind you, try to do what I just did. Make sure you check those conditions and then do those calculations. So based on a study by Gallup, 76% of Americans believe that the state of moral values in the US is getting worse. Suppose we obtain a simple random sample of n equals 60 Americans to determine which believe that the state of moral values is getting worse. Describe the sampling distribution. Which part didn't you write down? This right here. Are you the conditions? The rules? So my sample has to be less than or equal, or less than, not less than or equal to, less than 0.05% of the population. And then NP times 1 minus P has to be greater than or equal to 10. Those are the rules. Yeah. So go ahead and check your conditions and then do the math for the mean and the standard deviation. I'll give you a moment and then I'll work quietly behind you. All right, let me know how you did. Yippee, I'm assuming that means you did well. Yep, you went one more out than I did, but I got the same number as you. Good job, Jennifer. All right, good. So now we can actually do math with this. Now that we've calculated this, we've described our distribution, checked our conditions, we can do some math. Unless there's questions before we move on. Are there any questions? Y'all are rock stars. Fantastic. Okay. According to the Centers for Disease Control, and prevention, 18.8% of school-age children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-age children, ages 6 to 11, what is the probability at least 19% are overweight? Okay, so I'm gonna do my math. They didn't put it on the next page, did they? They did. Oh, I don't care. I'm gonna do the math anyway. And then the next page will give it to us, but I'm gonna do the math anyway. So I'm gonna do it down below. I'm gonna put A down below, and then I'm gonna erase it and do B. So I'm not gonna check my conditions. The next page will do that for me. We're gonna just assume at this point because I just wanna get to the math. All right. So first thing we have is that our mean sub p hat is going to be 0.188. Our standard deviation sub p hat is going to be 0.188 times 1 minus 0.188 divided by 90. Let me get that math. I got a standard deviation of 0.0412 approximately. All right. So now that I have these, one of the lovely things, jump into normal CDF and just use these values. I'm going to use normal CDF. We want to know at least 19%. So we're looking for probability that p hat would be greater than or equal to 0.19. That's what we're looking for. Probability that our p hat is greater than 19%. So I would put 0.19, 1E99, 0.188, and then our 0.0412. Once again, you can put the math directly into your calculator. You can use the fancy math directly in there. I'm going to jump to my other screen and show you that because it is beautiful, beautiful thing. And even if you don't choose to be fancy, it is okay. You don't have to be fancy. Okay. But I like to be fancy sometimes. So we got that already. We have 0.188, 188, and I'm going to clear this out and I'm going to be fancy. So we have, I'm going to put an extra parenthesis in here, 0.1, uh-oh, that's not what I want. Clear this out. I did something weird. Okay. Parenthesis, 0.188 times 1 minus 0.188, close my parenthesis, divided by 50, close my last parenthesis. That's 90, not 50. Okay, there we go. Now hit enter. And all of that is pasted in there, and it is lovely. And then I'm going to hit enter again, and it calculates it all for me. If you don't want to be fancy, I'm going to get the number that you're going to get if you're not fancy. Okay. If you're not fancy, you should get about 0.48. Actually, they're almost identical. Almost identical. So yeah, they are pretty close to identical. So I just did it on my calculator without the fancy, and they're almost identical. So my probability is approximately 0.4806. So that's approximately what it is. That's what I got on my regular calculator. So that's the probability that at least 19% are overweight. So when you are using when you're doing part B, I'm going to move this up a little bit if it'll let me. Part B, there's more than one way to do this. So, I could do a normal CDF with this and get the probability that 24 or more are overweight. So one way to do this would be probability p hat greater than or equal to 24 out of 90, whatever that is. So I could do that. That's 24 divided by 90, which is 0.266. I could do that, or I could take this standard deviation and I could multiply it by 2. Actually, that's not even the best way to do it. So my p hat is 24 divided by 90, sorry, which is 0.267. So what I can do is I could take my 0.188 plus 2 times 0.0412. This is the 2 standard deviation rule. So that we've done this before. So take a look here, 0.188 plus 2 times 0.412. What did I do here? Oh, I missed a 0. Like I ended up with a probability higher than, okay. So when I use the 2 standard deviation rule, I got 0.2704, unless I did that wrong. Okay. So this is almost an outlier, not quite an outlier. I'm going to try it with a normal CDF. Give me a second here. For some reason in my brain, I thought that it was an outlier. Let's see here. 0.267. Let me see. It's supposed to be an outlier. What did I do wrong? Anybody see me do anything, what I did wrong here? Okay, ignore this. I don't know what I did wrong, and I'm sure I did something wrong. So normal CDF, when I did 0.267 to 1E99, 0.188, and then 0.0412, I got a probability of 0.276. So where's my 2? There we go. So I got an unusually small number. I got that there's less than a 5% chance of getting a sample with the average of 0.267. So there's different things that you can conclude. What you can conclude is that maybe that particular area where they got their number, that sample, maybe it's like a food desert. Maybe what the Centers for Disease Control and Prevention said is wrong. Maybe the population standard deviation they gave us is wrong. That's possible. There's any number of things that it could be. Most of the time, we would just conclude that they were wrong. I'm going to go to the next screen with the math. Here we go. So we already got this. We got all of this stuff. Here they did their check. So my this shows independence. This shows that 90 is less than 5% of the population. So all of that is what we got already. And then coming here, they did a Z-score. They did a Z-score, and they did with their Z-score. But I believe that they got the same answer as me. Yeah. What might I conclude? So if it's less than 5%, I might conclude, is it going to tell me? I would expect about 3 samples in 100, resulting in that kind of a proportion. It is unusual, and you could just base your own conclusion. If you got some sort of a question that said, what can you conclude? Make up a story. Say, maybe the CDC is wrong. Or you can say, maybe they got an unusually large number of kids that were in a food desert or a high poverty area because they tend to eat a lot more processed foods. You just make up a story that makes sense. Questions? We're gonna do another example. We literally have one slide left. You guys have been awesome. I know this is a little bit longer class, but you've been awesome. Okay. Okay, I'm not gonna require you to don't do all of the checks. I just want you to do the math. So part A is just the regular, calculate your mean and standard deviation, do your normal CDF. So go ahead and start without me, and then I will follow behind slowly, quietly. 15% of Americans have hearing trouble, and a random sample of 120 Americans, what's the probability? At most, 12% have hearing trouble. So go ahead and do this calculations. Yes. Yes, Jennifer, that's exactly what I did. Because 1 minus 0.15 is 0.85. I just didn't have a whole lot of room, so I didn't write out the 1 minus. Right, how do we do with part A? We're do okay with part A? Yes, it's because it says at most. Well, no, the 0.85 and the 0.15, those had nothing to do with the at most. The at most part was just the less than or equal to. This all I did here is do right here. All I did was do 0.15 and then 1 minus 0.15. That's all I did, because 1 minus 0.15 is 0.85. It has nothing to do with the at most. I just did the math. Yeah. Yeah. How'd we do?
Okay, I guess I'm confused with the p hat is less than or equal to 0.12, or the p hat is greater than or equal to the 0.217.
Okay, so these are two separate questions, just using the same data. So because the part A says at most would be less than or equal to.
Okay,
So, and then the bottom one, because, I mean, we don't have a way to do exactly. And so, we just, less than or equal to wouldn't make sense, but we result in 26. If the p hat that I calculate is higher than my mean, I go greater than or equal to, because we're trying to look at an extreme number.
okay, thank you.
And
That
if
that
it
makes
was,
way more sense.
if I was saying, you know, what, that I had a random sample and only 2 people had hearing trouble, I would do less than or equal to, because it would be significantly lower than my mean.
Got it.
Does that make sense?
Yes, yeah, that makes a lot of sense. Thank
Yeah,
you.
Clint, I guess I could have told you that you got, if you do the fancy thing once, you got to do the fancy thing twice, but it's okay. You got this. You can be fancy. Even you can be fancy. All right.
I really struggle with trying to figure out where to put the percentage at on whether you use the -1 E99 or you use the 1 E99. Can you kind of
Well, if you're going less than, you're going down to negative infinity. If you're going greater than, you're going up to positive infinity. So if you think about like I don't think I have another, yeah, I do. So let's draw this. So I'm just going to pick a value here and highlight, that's not a highlighter, highlight down here. So if I'm thinking about a number line, think about the number line underneath of your curve. This way here goes off to negative infinity, way down there. It's going to go negative, like super, super, super negative. So that's, if I'm looking at less than, I need to use the -1 E99 on my lower bound. This one up here goes way big and goes to positive infinity, because it is getting super, super, super large. So if you're looking at a lower bound, if you're going less than or equal to, or at most, or whatever, it's got to go to negative infinity on your lower bound. If I'm doing greater than, I'm going to go super, super big, and it would be positive infinity. Does that help at all?
can you tell me what the word is in problem B that made you decide that the 0.217 needed to go in the negative slot?
There was no word. I mean, it's going in the positive. Oh, you mean on letter A?
No, for letter B, when you did the normal CDF 0.217 1 E infinity.
The reason it went in the positive slot, so because my p hat is significantly bigger than this p hat is significantly bigger than the population, than my population proportion, I'm going greater than, because if I use less than, it's going to include my population proportion. So drawing that picture, I'm going to draw it again. Let's clear all of this out. Clear all of this out. Okay. So on my picture, my mean here is 0.15. And the data that I have, I don't remember what it is, 0.217, has me over here. This is 0.217 right here. Now, if I was calculating using this down here, this is going to include my mean, and it's not gonna look anything weird at all. It's gonna be like, oh yeah, most of your data's down there. It is, it's including my mean, so therefore nothing's weird here. I need to shade the area that doesn't include the mean. So I need to shade the smaller area, the area that doesn't include the mean, because my value is significantly higher, that 0.217. I'm looking for the probability that I get a sample that has a proportion that is greater than or equal to that value, because I can't do just equal to. So I need to look at greater than or equal to. What's the probability that I land here or greater than that.
Okay, gotcha.
Yeah. Now let's say that I did a different sample and I was over here. Let's say that I got a sample that was 0.08. Then I would go less than, because to not include my mean, I'd be way down here and I'm significantly lower. So then it would be less than or equal to. So you just try the one that doesn't include your mean, go that direction.
So then if it's
Go
then if
ahead.
it's less than your mean, then it would be the negative 1 E99,
Yes.
comma, then okay.
Yes, exactly. So with letter B, a conclusion I might draw is because with the random sample was people who listen to headphones. There's a screaming baby outside your house. Because the people were using headphones, the sample of 120 Americans, and it would be really unusual to get 26 that have hearing trouble, it would lead me to believe that possibly using headphones could lead to hearing loss. And so that's probably the conclusion I would draw and say that maybe we need to study that. So that's my last slide. I do want to look at one homework problem, because actually maybe two, because definitely people have trouble with them. So I'm going to look at one or two and just kind of give you an idea of what's going on. And then I'm going to free you. Y'all have been troopers here. So let me go to my open math, which I thought I had open, but apparently I do not. I opened everything else. It's okay. I can get there quickly. Let us. Okay. So going down here, I'm going to look at 8.1. There's a couple of questions here that I get emails about pretty regularly. So I'm going to try to, okay, that's good. Okay, this is one of them. This isn't one where I was planning on stopping. Okay, so we have a random sample of 43 trees. You're going to calculate your mean. So your mean is the population mean. The standard deviation is your new standard deviation. Use your standard deviation divided by the square root of your sample size. These are just asking for the data values. This wants the mean in the middle, and you're going to use this standard deviation, and this value will be your mean plus two new standard deviations. This one down here will be the mean minus two standard deviations. You're just filling in the boxes for your empirical rule. Okay. Hold on here. The heck. Okay, this is the one. Now, different people have to solve for different things. This diagram is my sampling distribution. This mean is the population mean, but it uses your new standard deviation to get to these values here. Okay. So it's saying that I have a standard deviation of 24. So that's the population standard deviation. I am looking for the sample size. So what you want to do is to use the new standard deviation formula. I write it down right now, just a second here. So, I'm going to write it down and I'm going to show you. Okay, so the standard deviation sub X bar is this 151 minus 148. So it would be 3. So you're going to put that into that spot. And I know you can't see what I'm doing, but it's okay. It gave me a population standard deviation of 24. I'm going to go back to my other screen. That's not the other screen. So all I did was put my sigma sub X bar in for that, and I put 24 in for sigma. Now you're just going to use your algebra skills and solve for n. So you're just going to solve this and just get n by itself. You're looking for your sample size. That is the math that you're doing. You're just going to use those algebra skills and solve for that letter. That's what's happening here. Okay. This is the last one I'm showing you. So notice this one right here. It says a population has a normal distribution. This is my mean. This is my standard deviation. I intend to draw this sample. Okay, I haven't drawn the sample on the first one. The probability a single randomly selected value is less than 244. This is a single value. Use your normal CDF with your population standard deviation, your population mean. Now on the second one, I took a sample. Get your new standard deviation, then use normal CDF with your population mean and your new standard deviation. All right, that's it. I am done. I've kept you till almost 7 o'clock, but y'all have been amazing. I've been good class, good job. Do we have any questions for while we were still being recorded to share with the good of the group?
Just that my brain hurts.
I'm sorry. Sorry I hurt your brain. I promise you Tuesdays will be shorter. It's just I had to put all of chapter 8 into one class because of office hours on Tuesday. Okay, I'm going to stop the recording.